guys, it's Miss Maneely. Sorry I can't be in class today, but I'm going to go ahead through the lesson anyway, and we're going to continue with what we talked about on Friday about estimating a population proportion. So we're going to be developing confidence intervals based on sample proportions, or p-hat, but I'm also going to show you how to use technology, or how to use the functions of your calculator to compute the intervals. And just remember, though, that computing the interval is only half the battle. What you really need to be able to do is explain what the interval means in the context of the problem. So let's just do a quick review of what we did last class. Hopefully you guys have finished your warm-up by now. Determining the confidence, or determining the critical z value from the confidence level. This is basically where you take your confidence level. That's going to be your central probability. So like this is going to be a probability of 85%. And I'm interested in finding the boundaries of that interval. So I'm trying to find the z-star values, or the z-score values, that are on the boundaries of that 85%. In order to do that, I'm going to be using my inverse normal command on my calculator, but I have to enter in the area to the left of my lower z. And so to do that, I have to figure out the area there. So if I've got 85% in the middle, that must mean that I have 15% on the tails. And so basically what you do is you take 100% minus your 85 and you split it in 2. So 15 divided by 2 is going to give me an area of 7.5%. Now you can use your inverse normal command. So go to second distribution, choose inverse normal, and enter in your area of 0.075. You want to make sure that the mean and the standard deviation are both 0 and 1. And that should give you a critical z value. And remember, you can take the absolute value. You don't have to worry about the negative symbol. It's going to be 1.44. Last class, we determined the z-star that corresponds to a 90% confidence interval. That's 1.645. For 92, it's going to be 1.751. For 95%, again, we did this last class, that's 1.96. And for 99, it's going to be 2.576. Now, the ones that we use the most often are going to be the 90%, the 95%, and the 99. So if you can remember these numbers, it'll save you a little bit of time as we're constructing confidence intervals. Let's take a look at number 2. A cracker company is interested in estimating the true proportion of consumers who would favor a new gluten-free cracker over the original recipe. The company has selected an SRS of 100, so that gives us a value of n. And they found that 12% favor the new cracker, so that's a p-hat value, because that's from my sample. So the point estimate is right here. Remember, the point estimate is just the value that we're using to estimate the parameter. It's our sample statistic. So the point estimator would be p-hat. The estimate itself would be the 12%. To compute the standard error, remember, standard error is just the standard deviation that is computed from the sample data. So we're used to computing the standard deviation by taking the square root of p times 1 minus p over n. The only problem is I don't know what p is. So I'm going to use my sample value, which is 0.12 times 1 minus 0.12 over 100. And because it's going to be different every time I take a different sample, I can't call it standard deviation. I call it standard error. And in statistics, error does not mean mistake. I mean, I guess depending on the context, but when we're talking about margin of error or sampling error or standard error, we're talking about this understanding of natural variability. It's not even a problem. It's not a mistake. It's not really even an error. It's something that we accept and that we can actually control. So the next part says, suppose we want to determine a 90% confidence interval for the true proportion of consumers who would favor a new gluten-free cracker. Well, we got to check to make sure the conditions are met. And now there are 3 of them, so we've added a new condition. The first condition is that we have a simple random sample. And if I look in the problem, I do believe it says that we've taken a simple random sample. That is given. We don't even have to make the assumption. It's given in the problem. The second thing we have to do is check to make sure that we can use the standard deviation formula. If we are sampling without replacement, I have to make sure that my population is at least 10 times my sample size. So this is an assumption that we will need to make, that we are assuming that the population is at least 10 times my sample size, which would mean that we've got at least 1,000 consumers. And that's reasonable. The third condition is my successes and failures. So I need to double check that 12% of 100 is more than 10 and that the complement of that is also more than 10. So n times p, in this case I'm using p-hat because I don't know what p is. So we're taking 100 times 0.12. I know that's 12 successes, that's good. So if I'm dealing with 100 things, and I've got 12 successes, my number of failures is going to be 88. So you don't necessarily have to do n times 1 minus p. You can subtract your successes from your sample size. Okay, so both of those conditions are met. So I know I can use a normal distribution. Let's compute the margin of error. The margin of error is determined by two things. It's determined by my z star times the standard error. So in the last problem, we determined what the z star value would be for 90% confidence. So it was 1.645, and the standard error we determined to be 0.032. And so if I multiply them together, I get 0.053. Excuse me. So if I want to do a 90% confidence interval estimate, I'm going to start by writing down that it's a 90% confidence interval. You always need to make sure that you include the level of the confidence in your interval. So the 90% confidence interval estimate, I'm going to start with p hat, 0.12. And I've already computed my margin of error. So it's just going to be plus or minus 0.053. And then when I compute the interval so it actually looks like an interval, I always do the subtraction first. So I would do 0.12 minus 0.053, and that would give me an interval from 0.067. And then I do my addition, and that would give me the 0.173. Then you're asked to interpret the interval, and it basically just means I am 90% confident that between 6.7% and 17.3% of consumers will prefer the new recipe. And I think we had a question like this in our last class where we said, if the old recipe, if 20% of the consumers preferred the old recipe, do we have evidence to conclude that this recipe is less popular? And if I look at my interval, I can see that between 6.7% and 17.3%, I'm pretty confident that that's somewhere in that interval is where the true proportion lies. Since both of those values are less than 20%, I'd be able to conclude that this cracker is less popular than the original. If 20% was included in the interval, though, I wouldn't be able to do it. Okay, so like I said, for today's lesson, we're going to continue with constructing confidence intervals for proportions to estimate a population proportion. We're also going to be able to determine the sample size required to obtain a certain level of confidence for a specified margin of error. And I'm also going to show you how to do this using your calculator. So in our last lesson, like I said, we talked about estimating a population proportion using a confidence interval. Because we're using a normal distribution, we're going to be using a z star or a z-score value. So oftentimes a confidence interval estimating a single population proportion is nicknamed one proportion z interval. In fact, on your calculator, it's called a one prop z interval. So it's just another way to describe the interval itself. Once we find the critical z values, our confidence intervals are always going to be in the same form. Our statistic in this case is p hat plus or minus our margin of error. So remember, this whole quantity here is our margin of error. And so to compute it, I find my critical value, that's my z star based on my confidence level, times the standard deviation of the statistic. And again, we call that the standard error when it's based on my sample result. So I'd be using p hat times 1 minus p hat over n, and that's going to be under the square root. And that's the next slide, actually. So go ahead and jot that down at the top. And we know that z star is the critical value for the standard normal curve with c% of its area between negative z and positive z. Okay, let's take a look at an example. It says the Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. I would not be surprised if that was slightly biased, depending on how that survey was done. Anyway, you are asked to construct and interpret a 98% confidence interval for the proportion of all teens who would say yes if asked that question by their parent. So the first thing we want to do is check conditions for inference. And remember, there are 3 of them. The first is that we want to make sure that we're dealing with a simple random sample. And I can see that that is given to us in the problem. It tells us that there's a random sample, so I can say that that is given. So that condition is met. The other condition, since we are sampling without replacement, I want to make sure that my population is at least 10 times my sample size. So at least 10 times 439. And so we're saying that we need to have at least 4,390 teens. I think that is totally plausible, so we can assume that. And then our final condition is the large counts. We need to make sure that we have enough successes and failures that we can proceed with inference using a normal distribution. And so remember we said that you need to have at least 10 successes and 10 failures. So sometimes we actually compute n times p and we figure it out. Now it corresponds to our expected number of successes. But in this case, I know how many successes there were. There were 246. So we had 246 successes. That is more than 10. Check. And since my sample had 439 in it, if I just subtract 439 minus the 246, I know that 193 of these students said no. And that, again, is more than 10, so that condition is met also. You could certainly compute your p-hat and then multiply by n, but you'd be back to where you started with the 246 successes. Okay, so let's go ahead and compute this interval by hand. And I don't have a ton of space here, so I'm just going to kind of do it underneath where it says letter C. So the p-hat we already know is 0.12. So let me go ahead and start off. Let's see, we want a 98% confidence interval. And so I've got my sample. I don't know where I got the 0.12. I lied. It's not 0.12. Let's figure out p-hat. So p-hat in this case is going to be 246 over 439. Let's go figure out what this is. 246 divided by 439. And I get 0.5604. So because this isn't an even value, and because I want to show you how when we do this using the calculator, we're going to get exactly the same numbers, I'm going to store this value. Oops. I want to store this value in a variable. So I'm going to store this in letter A. When I write it on my paper, obviously, I'm going to use my estimate of 0.56. Plus or minus. Now I've got to figure out what the z star value is that is associated with a 98% confidence interval. And this is not one of the ones that we had in our warm-up, so I've got to figure it out. So if I'm dealing with a 98% confidence, that's my central area, then I know that the area underneath, the area in my tails has got to total 2%, so the area under one tail is going to be 1%. So let me go ahead and compute my z star value for that. So I go to second, distributions, I choose my normal or my inverse normal. I'm going to enter in my area of 0.01. And then I'm going to compute my critical z value. And again, this isn't a whole number, so let me go ahead and store this. Actually, I don't want it to be negative. Let me multiply by -1 for a sec. All right, so I want to store this value in alpha b. Okay, so my p-hat I stored in letter A. My z star is 2.326, and I stored that in letter B. So my z star value would come next, 2.326. And then I'd need to compute my standard error, which is going to be the 0.56 times 1 minus 0.56 over n, which is 439. Okay, so when I actually do the math, I like to do it all in one step. So I don't like to compute my standard error and then round that number and then multiply it by z and then round that number to get my margin of error. I kind of like doing it all in one step. So remember, I stored my 56% in alpha A. So this is an alpha A, this is an alpha A, and I stored my z star value in alpha B. So when I compute this on my calculator to avoid any rounding error, I'm going to start with my estimate, alpha A, and I'm going to do the subtraction first. So I'm going to do minus my z star, which I stored in alpha B, and then I want to multiply that by the standard deviation, or the square root of alpha A, And then in parentheses, I'm going to do 1 minus alpha A. And then I'm going to end the parentheses and divide by n, which is 439. And when I do this, this is going to give me my lower bound. So my lower bound is 0.505. And then if I just hit second enter, it'll call the whole command back up. And all I have to do is go back and change that A minus B to a plus. And that'll give me my upper bound, which is 0.615. And so in conclusion, I would say that I am 98% confident, right? That was the confidence level. Yes, let me go ahead and write that. I am 98% confident that between 50.5% and 61.5% of teens, I'm going to say would respond yes to the question. Okay. All right, and that's how I would interpret the interval. Now, the moment you guys have all been waiting for is how can I save time and just use the calculator to compute my interval? It's very, very simple. So let's take a look at the instructions on your paper. It says to find the one prop z interval command, and to do that, you're going to go to your stat button and then scoot over to where it says tests. So hit stat and then scoot over to tests. And notice that you have a bunch of tests in the beginning of your screen, and then if you scroll down, you'll start to see commands for intervals. So we're going to find the one prop z interval. It should be letter A if you have a newer calculator. One prop z interval. You'll see that there are two prop z intervals, and that's for like if we're comparing two populations, I can use the two prop. Okay, now when we're entering in the values, we need to be very careful. Notice how it's asking for an x value. It must be entered as a whole number. So for example, if I tell you that p hat is 12% and I'm dealing with 132 people in my sample, taking 12% of 132 may not produce a whole number. And so you need to make sure that whenever you're doing this command that you're always entering in a whole number for your number of successes. Because remember, oftentimes our p hat value has been rounded. So you want to round back to get the number of successes. So in this case, I had 246 successes. That's how many students said yes. My sample size was 439. My confidence level, make sure you enter this as a decimal, is 0.98. And if you press enter, you should get your confidence interval. And notice that it gives it to you in the form of a confidence interval. So it gives you the lower bound and the upper bound. It gives you your sample p hat value. It also tells you your sample size. What it does not tell you is the value of your margin of error. So if you wanted to compute your margin of error, that would be the distance between p hat and either one of the ends. You'd either need to subtract or you'd need to compute. So like if I wanted to find the margin of error, I would have to simply do, I'd subtract my interval. So 0.615 minus 0.505, and then I would divide by 2. So it's handy to use the calculator to construct your interval, but you still need to be able to tell me what a margin of error is. If I ask you to compute a standard error, you should be able to do that too. So don't rely totally on your calculator. Make sure you understand each part of the formula to be able to compute. Okay. The next thing I want to talk about is how to determine an appropriate sample size. So for example, if I want to make sure, and actually let me look at an example. That's not going to help me. All right, let's go back. So if I want to determine the size sample that I would need to stay within a certain margin of error, because a lot of times we want to control the margin of error. We want to set it to be no more than 5% or no more than 3%. And so I have to figure out what sample size to choose. And so if I'm given a margin of error and I'm given a confidence level, I want to figure out, and basically it's just the same formula. Remember, our margin of error is made up of two parts. It's made up of a z-score, and it's made of my standard error. Well, the standard error formula requires us to have a sample proportion. But if I haven't taken my sample yet, I don't have a sample proportion to use. And so what we end up doing is using 0.5 because that is the largest possible value that we could use. It's going to give us the greatest standard error, and so it's going to keep us on the safe side. So here's basically the rule of thumb. If P is given, use it in the formulas. If it's not, use P hat. If P hat is unknown, use 0.5. Because that's going to give us your greatest margin of error. And so that way we make sure that we're getting a sample that's large enough to stay within the parameters of the problem. And so that's the sequence. If you know the population proportion, make sure you use it in all your formulas. If it's not given, then you can use your sample proportion. If you haven't gathered your sample yet, then use 0.5. And so let's just do some examples. I'm going to do one with you. And then I'm going to let you do a couple on your own. So in practice, so it says, Miss Quinn's class took an SRS of 102 pennies and discovered that 57 of the pennies were more than 10 years old. Check that the conditions for inference are met. So again, do we have an SRS? It's given in the problem, so we can check that off. Number two, we need to make sure that our population of pennies is at least 102 times 10, so that's 1,020 pennies. Again, that is a completely reasonable assumption. And we already know how many successes there were. We have a number of successes is 57, and that's more than 10. And that means my number of failures, if I had 102 pennies, that means, let's see, I had 45 failures, which is also more than 10. So that condition is met as well. So let's go ahead and do this on the calculator. I'm going to go ahead to my stat, test, and I'm going to scroll down until I find my one prop z interval, because I'm dealing with one proportion and I'm dealing with a normal distribution, so I'm talking about z. Okay, the number of successes was 57 pennies. The total number of pennies was 102. The confidence level in this case is 99%, so make sure you enter it in as a decimal and calculate. Easy peasy. And so we've got our interval itself. Make sure you include the confidence level. So we have a 99% confidence interval is going to go from 0.432 to 0.685. And so if we're asked to interpret that, we can say we are 99% confident that between 43.2% and 68.5% of all pennies are more than 10 years old. Okay. And so in letter C it says, is it plausible that exactly 60% of all pennies in the collection are more than 10 years old? So we want to look to see if 60% falls in or out of our interval. And since it falls within our interval, it's completely plausible that that is the actual population parameter. If it was 70%, the answer to the question would be no, because I'm 99% confident that it's going to be within 43 and 68. So if I'd say, is it plausible that 70% is reasonable, the answer would be no. So since 60% is contained in the interval, and let's go ahead and be precise, in the 99% confidence interval, it is plausible that it is the true proportion. Oops, I'm not spelling anything correctly now. Okay, number 2 asks us now to determine a sample size. So it says, suppose Ms. Quinn wants to reduce the margin of error to less than 10%. So again, our margin of error formula looks like this. Our margin of error is equal to z star times the square root of p times 1 minus p over n, or in this case, p hat. And so I'm saying that I want my margin of error to be less than 10%. So I'm going to go ahead and exchange my margin of error for 0.1. And if I want it to be less than 10%, then I'm going to use I know this might be confusing. I'm going to use a greater than or equal to sign because I want this quantity to be less than 10%. And so if I'm doing, again, a 99% confidence interval, my confidence, my z star is not going to change. And so if you remember the z star value associated with 99% confidence, let's see, where's that table? So 99% confidence, I would use this z star value, 2.576. Sorry. So 2.576. And then I'd have my p times 1 minus p. The n is what I don't know. I don't know my sample size. So I'm going to keep that as a variable. But I also haven't taken my sample yet, so I don't have a p hat to use either. Well, I only want to keep one unknown in this problem. And so since I don't have a p, I don't have a p hat, I'm going to use 0.5. So in this problem, I would go ahead and just use 0.5 to estimate my sample size. Now, I'm going to actually do this problem on another slide so you can see exactly what I'm doing. So we got 0.1 is greater than or equal to 2.576. And then we've got 0.5 times 0.5. All of that is over n. So why don't I do this? Why don't I separate my square roots? This is the same thing then as 0.1 is greater than or equal to 2.576 times the square root of 0.5 times 0.5 over the square root of n. I haven't done any math. All I've done is I've just rewritten it so you can see that it's just a proportion. And we've seen proportions before. If I am trying to solve for n, then I can essentially switch these two terms because I'm going to multiply both sides by the square root of n, and I'm going to divide both sides by 0.1. So I can rewrite this formula to be the square root of n is greater than or equal to 2.576 times the square root of 0.5 times 0.5, which is just 0.5, but we'll get there in a minute. And that's going to be over 0.1. So let's go ahead and do that math. I'm going to type in 2.576. I'm just going to type it all in. I'm going to have my square root of 0.5 times 0.5. Make sure you come out of the square root before you do your division. And that gives me 12.88. Now I got to be careful because that corresponds to the square root of n. To figure out n, I'm going to need to square both sides. So n has to be greater than or equal to 165.89. And since I can't take a sample of 165.89, you always want to round up. And so I want to take a sample of 166, and we're talking about pennies. So make sure you use appropriate units. Okay. There are 2 more problems that follow. I would like you to pause this video and spend a few minutes answering questions 3 and 4. Okay, so let's take a look at problem number 3. Parts A and B we did on Friday. So if you wanted, it says Ms. Quinn's other class constructed a confidence interval for the proportion of pennies that are more than 10 years old using a different random sample of 252 pennies. The following interval was obtained. So you're given the lower bound and the upper bound. If you find the average of those two numbers, you're going to get p hat, which is 0.516. The margin of error, if you take the difference of the interval and divide it by 2, is going to give you the margin of error of 0.062. The next question is tricky. What confidence level was used to construct the interval? So here, let's just plug in what we know. I know the margin of error, right? We figured out the margin of error. This is my margin of error. And that's going to be equal to z star times my standard error. And that's what we've got here. I've taken my sample statistic, 0.516 times 1 minus 0.516. I've divided by n. So that's my standard error. So what I want to do is just solve for z star. And I'm going to do that simply by dividing both sides. I haven't done this very well. I'm going to divide both sides by this huge fraction here. I don't even care that I've got the radical. I don't care that it's all, that it's a huge expression. I'm just going to take 0.062 and I'm going to divide. Now make sure when you're dividing that you do put everything in parentheses. So, I mean, in this case, it's no big deal because the whole thing is under the square root, but I am going to put the whole thing in parentheses because you'll need to do this when we get into means. So I have my 0.516 times 1 minus 0.516. I'm going to close the parentheses, and then I'm still dividing by the 252. And when I do that, I get this number. That is my z star. 1.9694. That is my z star. That should look somewhat familiar. It's very close to the 1.96 that we use for our 95% confidence interval. Well, if I want to know the exact confidence level, let's think again what this number refers to. My confidence level is my central probability, and in this case it's unknown. But if I know my z star value, then I know that it's going to go from a negative 1.9694 to a positive 1.9694. And in this case, if I know my z-score, then I can compute the area under the curve using a normal CDF function. My lower bound is going to be negative 1.9694, and the upper bound would be a positive 1.9694. Use 0 and 1 as your mean and standard deviation. And my confidence level is a little bit more than 95%. Okay, so you do need to be able to do the math correctly. And so you do need to be able to show me that. In the last question, number 4, this is what a computer output looks like. And notice that it says it's a z interval for proportions. It tells you with 90% confidence, and then it gives you this. In this case, it's your confidence interval is expressed as a compound inequality, where our lower bound is 0.299 and our upper bound is 0.469. You're asked to interpret it or carefully to explain what it tells you. And basically, we can say we are 90% confident that between 29.94% and 46.98% of all cars are made in Japan. Okay. So what I'd like you to do now is I'd like if someone could grab the study guides for this chapter. I kind of wanted to wait until we covered enough material that it would make sense to start filling this in. But to sort of wrap up the lesson in and of itself, what I'd like you to do is look over your notes from last class and today, and I'd like you to answer questions 1 through 5. And I'd like you to fill in this first block where it talks about population proportion. If you also look back at your notes from last class, you can interpret these two things, interpreting the confidence interval versus interpreting the confidence level. So I'd like you to go ahead and fill that in. And then once you've finished filling in the study guide, I'd like for you to go ahead and start working on the homework exercises. There are quite a few. I don't expect you to finish them in class, but I do expect you to at least get started on those homework problems in class and then finish the remaining problems for homework. And obviously, if you have any questions, come and see me in Bulldog Block. I'll be here on Wednesday. For those of you that are still interested in getting help for the retake, just come on into Bulldog Block and we will get you help. Have a great day, guys.